Hello and welcome to this talk about what's beyond 1001 data service instances. So why do we need this talk? Well, from designing data services for a while and observing others doing the same, we had the perception that automating data service is a challenge task, and that especially during the early stage development is driven by feature demand. So developers are focused on identifying and developing features as demanded by the target audience, such as accessibility of service instances, backup and recovery, embedding into existing network and security policies, and so on. But platforms out there, for example large IoT platforms of Industry 4.0 companies, are likely to grow to significant scale. And looking at software development, a little like driving a motorcycle, you have to know what's right in front of you, what we call being driven by the feature demand. But in order to drive your motorcycle smoothly, you also have to look ahead. And you have to be in a constant change of looking right in front of your wheel and looking into the next corner. So we would like to look into the next corner in this talk and find architectural bottlenecks and learn about them and improve them. As our mission is operating Cloud Foundry data services at a scale. So what does scale mean? Especially as there are so many possible data service designs. There's so many decisions to make. What resource types to use, what kind of provisioning you want to have, like pre-provisioning VMs or provisioning them on demand, like how to perform failovers, providing data redundancy, or just keep a single replica, which automation technology to use, and so on. Also, there are quality factors that may differ between implementations of data services, such as the desired time to repair, the accessibility of service instances, the way the solution integrates into your network security, whether to use encryption or not, the availability of your data service, the performance, the operability, the transparency, and so on. So in order to actually narrow down the discussion around how to achieve a service with more than 1,000 instances, we have to define some constraints. So one of which is the question, what is a service instance going to be? And answering the questions, what is the total number of service instances we'd like to have? Obviously, more than 1,000. But the third question is not that obvious, which is how many service instance operations we would like to allow happening simultaneously. So let's say you have 10 developers, each of which creates a single data service instance. You have 10 data service instances to be created simultaneously. So in the following, we would like to look at the common data service design patterns and look at their particular scalability, then pick one of them and go more into the details on how to scale that particular infrastructure, that particular data service architecture. While there are so many different design patterns, as you can derive from this space of options presented before, 3 are currently very common, so it makes sense to have a closer look. So the first obvious is a shared VM cluster, then dedicated containers, and then dedicated virtual machines and clusters. So let's have a look at their scalability behavior. So looking at the shared cluster, what is a shared cluster? In a shared cluster, you have a cluster of virtual machines, in this case 3 virtual machines, creating a MongoDB replica set. So you are using asynchronous replication to replicate the data from the MongoDB server to 2 other servers so that you have a standby and you'll be able to perform a failover. For Postgres, there will be a master-slave setup, preferably 1 master and 2 slaves, and some kind of cluster manager that allows you to perform a failover automatically. Most of the time, these virtual machines are pre-provisioned, so you have to decide during the setup how many virtual machines you'll actually have. Right, so now you have your MongoDB cluster, 3 virtual machines. What to do next? Well, you actually slice up this cluster into several data service instances. So each database is going to represent a service instance. So the databases are created on the cluster are then represent service instances. This approach is very simple to implement, and the cost of the service instance is very low. By creating more and more instances, the cluster utilization increases, and at some point, the cluster will be overloaded. So the shared cluster comes with low cost per service instance, and it actually comes with a simple service broker logic, because all you have to do is create a database when creating a service instance. And when creating a service binding, all you have to do is create a database user. The drawback is that it has weak isolation. And that is true for most of the data services, as only few data services come up with production-grade isolation mechanisms, allowing you to separate data service instances from another using the capabilities of the data services, such as a Postgres database provides some kind of isolation, but still the behavior of other databases on the same cluster are likely to influence the behavior of other databases. So there is no strong isolation. There's no proper bad neighborhood protection. So also, the fact that a cluster is pre-provisioned, hence there is a certain amount of infrastructure resources dedicated to this cluster, which will then be used to slice up service instances. Naturally, this cluster is going to be full at some time. So what are you going to do when the cluster is full? So one idea could be to just add another cluster and add more service instance to that cluster too. Well, while this is possible, your simple service broker logic goes away because you have to deal with several problems such as fragmentation, which happens when there's a frequent creation and deletion of service instances, causing a placement problem. When clusters aren't fully loaded, you have to decide when creating new service instance where this service instance is to be placed. So you need a strategy to place new service instances, and that requires data service specific logic. So let's have a look at this particular scenario, and assuming that one of the clusters becomes more and more empty, the entire cluster could be rebalanced by moving the service instances to another cluster, and thus freeing the used infrastructure resources would be desirable, because what you can see here is a great waste of infrastructure resources. It's in general unbalanced set of cluster waste infrastructure resources. So we would like to perform that rebalancing to remove that cluster and free those resources. So what's the conclusion for shared clusters? First of all, the scalability issues here, they can be addressed. It comes with the price of increased complexity in a service broker, but it's possible. The isolation issues, on the other hand, they are heavily data service specific, as some data services don't have isolation and tenant capabilities at all. For example, Redis. A generic solution also is not possible. You have to think about how to isolate service instances on a per data service type level, which is very bad when designing a framework to integrate a large number of data services over time. So one alternative approach would be to have a solution based on containers, providing a better isolation. So instead of a cluster of setting up a Postgres cluster, you'll have two virtual machines, let's say being equipped as Docker hosts, and whenever you create service instances, you create containers or clusters of containers. So in that example, you have a two container cluster of Postgres databases being replicated using asynchronous replication. Of course, there is increased complexity in orchestrating the creation of containers, as well as setting up the asynchronous replication. In this scenario, you should also be aware that two virtual machines are actually not a good choice for a database cluster, because you'll be subject, or you'll be vulnerable to network segmentations, and a cluster algorithm wouldn't be possible to make a unique leader election, because there's no quorum possible. So the preferred solution to this would be also to have 3 instead of 2 nodes. All right. So looking at that idea of having 2 Docker hosts, creating Docker containers across those 2 hosts, you'll run into a similar problem when scaling that solution, because at some point the cluster will be full. And as those Docker hosts need to be set up before being able to use it as the foundation of your data service solution, you run into the same structural limitation. So answering the question of what to do when the cluster or the Docker hosts are full is about the same. You could actually think of just adding another one, but then you have the same service broker challenge. And as I said, it's possible to do that. But how do you add those cells on demand? So let's say your cluster is full in the middle of the night. You just have to wait until your sysop wakes up, or you have to wait until the next morning. And still then, you have to create VMs in order to scale the system. So preferably, that would happen on demand automatically. So why not delegate all this complexity in the first place and leave most of it out of the architecture? That brings us to the third common data service pattern, which is on-demand dedicated virtual machines and clusters. So with that approach, what you do is comparable to a shared cluster. You create a cluster of virtual machines, let's say 3 virtual machines comprising a MongoDB replica set, or 3 virtual machines comprising a master-slave-slave Postgres setup being asynchronously replicated. But in that case, this particular cluster is not the foundation to create service instances, but it is a service instance itself. So what you do is, whenever somebody says CF create service, you create such a cluster on demand. A real-world implementation of that should allow the creation of single server instances as well, in order to allow smaller databases to be created, as a cluster is, of course, using infrastructure resources and might be costly. So service instances are represented by a single VM or a cluster of VMs, which allows you to have a stronger isolation and dedicated infrastructure resources. A service instance must be a Postgres master-slave cluster or a MongoDB replica set in that case, or as you can see in the lower right corner, a single Postgres or MongoDB server. So now, while this sounds like a lot of complexity, how can the on-demand provisioning of clusters be a simple solution? The answer to that is we delegate the heavy lifting. So looking at an exemplary architecture, you can see that basically the service broker can be a generic component that's entirely independent from the data services you're actually implementing here. So whether it is MongoDB, Postgres, Redis, Elasticsearch, same service broker will be used. One specific class that will be implemented per service type is the so-called SPI, being responsible for creating credentials, as this is a data service specific task to do. However, whenever you create a service instance, what the service broker basically does is talking to a deployment component which manages the deployment of instances using Bosh. So what this solution basically does is it triggers Bosh deployments on demand. And this allows you not only to provision those virtual machines on demand, but also allow you to be infrastructure independent and also get all the self-healing capabilities that come with Bosh. You can define several different service plans by mapping service plans to Bosh releases, in this case Bosh manifests. So as you can see, there's a single MongoDB and a MongoDB cluster, and they will be provisioned based on the same Bosh release, and the difference will be how the Bosh manifest is configured by the solution. So most of the heavy lifting when it comes to virtual machine orchestration, for example, where to place the virtual machine on the infrastructure, ensuring that every infrastructure virtual machine is placed in the right availability zone, it's all handled by Bosh. Your deployments are going to be infrastructure independent. Your data services also going to be operating system independent. You'll have several self-healing capabilities inherited from Bosh right away. Talking about the placement problem and the fragmentation problem, that's not ours to solve, as this is a problem the infrastructure layer itself has to solve. So we just delegate that problem and take it out of our architecture. So what are the remaining challenges approaching 1,000 service instances? Basically, when you create clusters, let's say 3-node clusters, you might end up having 3,000 virtual machines. So how do we get there? How can we assure that our architecture is able to do that? Of course, you could naively just spin up 1,000 service instances and see what happens. But that's an experiment that could become very costly. So we actually try to be prepared and took advice from the lean startup, where the main paradigm is to build, measure, learn, and do that within a loop. And the loop exits when you found a product market fit. So applied to our challenge of creating a data service for more than 1,000 service instances, how can we actually adapt that paradigm to our purpose? In this case, we took our MongoDB implementation based on the architecture shown before, and we are looking for one MongoDB that supports more than 1,000 service instances. So the questions to be answered is, what do we have to measure? And what do we have to learn from it? So while answering the question, we've been searching for hypotheses of potential bottlenecks. That's why we had to look at the architecture again, and by creating a system dependency graph, we tried to find potential bottlenecks and derive them from the architecture. We came up with the following list. So basically, every service framework component could be a bottleneck. Bosh itself could be a bottleneck. For example, the director VM, the number of workers, the nuts message bus, or maybe the infrastructure itself. Just by thinking of what happens behind the scene, Bosh and infrastructure were the two very likely to be influencing factors as they do the heavy lifting. But we don't know yet. So we would like to define experiments to find out. In order to see whether a certain scenario actually works, we have to define quality attributes that allow us to judge whether a certain scenario works at a certain scale or whether it doesn't. So we from the patients being observable by a developer, we thought that creating a service instance on demand, being provisioned on demand, 3 minutes is a good way. It's worth waiting 3 minutes to get a dedicated virtual machine. We have to also accept a certain derivation from this duration, because whenever the platform becomes utilized a little more, things might take a little longer, which is kind of natural thing, but there has to be a boundary. You don't want to wait 3 hours for a service instance, so we try to start with that first guess, 3 minutes and 200% derivation. So well, actually what we did is a 300% derivation, so we actually allow up to 9 minutes. Service instances. The two things that do impact is the number of service instances you want to be able to run in total, but also the number of service instance operations. And both depend on the scale of your deployment of the data service solution. So in order to find out how to scale it and see what performance it will be able to cope, we need to identify relevant metrics and logs so that we have real measurements, data that we can learn from. So we are going to look at the system behavior. We need data to identify and explore the bottlenecks. We looked at our architecture and thought that Bosh is doing the main work, so we have to look closely at Bosh. For example, how long does it take for a service instance to be created? Which breaks down to the question, how long does it take to perform or to execute a Bosh task in total? From the point in time where I executed the cf create service command until the service is created. We call that the lead time. Also, in case that there are several operations simultaneously executed, we have to accept that there's a potential queuing resulting into a wait time, a time a Bosh task resides in the Bosh queue waiting for execution, as well as the execution time itself. We also call that the cycle time. And of course, we need the system metrics from all virtual machines and components participating in that use case. So, how do we gather relevant metrics and logs? We co-located a log stash on every virtual machine of the relevant components to receive the system metrics, and we also scripted the Bosh CLI to gather the relevant timestamps for the Bosh tasks. So a feature request to the Bosh team here is, it would be very nice to have these values available via API or even streamed to a metric component. So we can stream that to our Grafana, whatever we use to do that, or Logstash. All right. So after that, our experiment looked like this. So our build, measure, learn loop, we start with our implementation. We have measurements from Logstash and the Bosh metrics, and we would like to learn whether our expected bottlenecks actually occur and when they occur. So looking at the scale of our system, what are the major influencing factors? So again, having a glance at the architecture, the scale of the anynines components will be influencing. the scale of Bosh will be influencing, and of course the scale of the infrastructure will be influencing. So there are there's different system behavior. For example, when you have one service broker and one deployer being located on a small virtual machine, including a Bosh with 3 workers running on a virtual machine with 4 gigs of RAM, compared to a Bosh with 10 workers, or 2 service brokers, 2 deployers, and a larger Bosh and even more workers. So we'd be able to have a rule of thumb scale-out formula that allows us and our customers to estimate the correct dimensioning of the system corresponding to a certain service level agreement. So we would like to find a pair of a system scale matching a certain service level agreement. So we started doing some experiments, and on vSphere we did the first experiment with a small setup. And as you can see, the creating a single service instance is easy. It just takes less than 3 minutes. Creating 10 simultaneously takes 6 minutes and 10 seconds, still passing our quality test. So you have to wait on average 6 minutes as a user until your service instance is created, when 10 users are creating service instances simultaneously. What you can also see is that there's a slight increase in the pure execution of the Bosh task itself, up to 4 minutes and 10. So the outcome of iteration was that this scale is suitable for creating up to 10 single server MongoDB service instances simultaneously if the user accepts to wait around 7 minutes in average. So sometimes it's 5, sometimes it's 9 minutes upon the creation of a service instance. We also confirmed by looking at the metrics that the anynines service broker and deployer is not a bottleneck, obviously, because they don't do much of the work. Which also confirms the second assumption that our Bosh is the dominant factor. And the conclusion from that is that we are going to scale Bosh for the next iteration. And we do that by adding more workers, because that's what the queuing time actually influences mostly. All right, so second iteration also happening on a small vSphere. We increase the number of workers, and as you can see, the total number, the total time required to create service instances, 25 here, compared to the one earlier, decreased from 60 minutes 52 to 30 minutes. But surprisingly, the Bosh task execution time varies from 3 to up to 8 minutes and 30, and that is somehow odd. So what's the outcome of iteration 2 is that there's a large derivation on the completion of the Bosh task, the Bosh execution itself, and that is caused by the infrastructure itself. So we learn that a small infrastructure may become a limiting factor when it comes to simultaneously creating virtual machines and here service instances. So the conclusion for us is we want to learn about the data service architecture and the data service automation. We use rather large infrastructure and move on our experiments to AWS. So we did the same experiment on AWS. And the result is clear. You see that the Bosh execution, whether you are creating 1, 10, or 25 service instances simultaneously, the pure execution time of a Bosh task is about the same, and it remains pretty stable. So the overall time required to create 25 service instances increases just from 3 to 5 minutes, or passing the quality test. The result of that iteration was that there is a little derivation on the completion of the Bosh tasks caused by AWS, and that a small infrastructure may become a limiting factor regarding the number of simultaneously service broker ops. Scale number 3 is also suitable for creating 25 single-server MongoDB service instances simultaneously, and it's likely that more operations are possible. So our next experiments are about increasing the number of simultaneous create ops until Bosh queuing is observed. And then we're going to take a step up and create a larger and scaling out Bosh even more and repeat that behavior. So that's where we currently are. And our temporary conclusions from what we've seen so far is that setting up the experiments took way longer than expected. So we are not there yet. 1,000 service instances haven't been created, but the architecture seems to be suitable. The number of simultaneously service broker operations, creating service instances simultaneously, is more challenging than the total number. So it's a fairly different thing whether you want to create 1,000 service instances at once or, let's say, over 2 weeks. So simultaneously service broker operations are determined by the scale of Bosh and, of course, by the infrastructure itself. Still, we are looking for a scale-out formula, even if it's only a rule of thumb formula, balancing the scales of the infrastructure, the runtime, the size of the runtime, the size of Bosh, the size of the data service components, in order to provide a reliable service level agreement for your particular use case. So we can conclude that the groundwork is done. We are now equipped to create larger experiments, and we will go on doing so. So stay tuned for results and feel free to ask questions.